You need not say more. Yeah. All right, thank you.
I can say. Yeah.
All right. So this talk is like Saturday morning, right?
Yeah.
Not meant to be serious, right? But nevertheless, if you have questions, do ask. All right. So now that you know about the title, and you know about the title of this slide, what do you think this talk is about? Some heavy words there. Ken? Yeah, it's close, but not quite. Yeah. Models, right? Yeah. You know who she is? Oh yes, Aishwarya Rai. She's like a top Indian model, right? Or used to be anyhow, when I was growing up. But yes, seriously, I mean, certainly about models, right? Models of certain kind. This is a great book, favorite book of mine. Everybody recognizes the three models here? Yeah? So this one? The wave equation. So that's the wave equation, right? So c is the wave speed. This, of course, and of course, right? Ian Stewart, great mathematician. Can you know him personally? Yeah. Yeah, I grew up reading his books on symmetries, and he has 17 equations. How many from control? Systems theory. Yeah, 0. I mean, I was bummed about that, but you know, it's okay. Yeah, I mean, he has Euler-Lagrange equation, and so. Anyhow, yes, that's a different talk. All right, so problem with Ian Stewart's book is a different talk. So let's move to the next subject, right? So I don't want to be accused of sexism here, right? I mean, so women models and men models. Yeah. All right. So if anybody doesn't recognize who this male model is, you can always shout out the name, right? This always dawns on you. And that goes with everything else. I mean, anytime you want to interrupt or shout something, just go ahead, right? Do it. So anyways, I was thinking about models. It's a serious question, right? So I'm thinking like every model has two attributes which are very, very important, right? So the most important attribute of a model is beauty, right? All right. Again, I'm not being sexist at all, right? Men and women, and all other sexes in between, the whole spectrum. And I've sort of drawn it as an axis. Anybody has any idea what the second one would be? Oh, I give it away. I give it away. Yeah, I give it away. I give it away. Yeah, next iteration or talk, I would have beauty and ... Anyhow, so utility. Again, right? So these are axes, so because they're a continuum, and of course the quadrant here is pretty and useful. So they're models, right, who are pretty and useful, right? You know, very pretty. She grossed 3 billion, or her movies that she starred in grossed $3 billion last year. Enormous impact, right?
I have a horrible feeling I'm going to be in the bottom left.
You know,
You're really testing our friendship.
you know, I mean, this says something. You know, this is how little my friends think of me. You know, or my judgment. You know, I mean, I haven't even put it here. Ken, I love you, man. I mean, you know, I'd never do that to you, right? Never do that to you. Of course, you can be pretty and useless, right? And of course, you can be pretty ugly and useless, right? You know. Now, yeah, we need that, right? Now, you think, you know, this guy's not a model, but I could not think of somebody who is more ugly, more useless than this guy. Yeah. Ken, in case you're wondering where you are, that's coming. Okay, anyways. But you know, don't worry, this talk is about math models, right? And you know, growing up, I mean, since my even school years, right? I mean, I always found this fascinating that there was always a connection between a beauty of a model or a concept, right? So each point here is a model about a scientific idea. And I'll give an example. As these things get more beautiful, they also get more useful, right? There's a positive correlation between the two. So I want to sort of talk about that when I come to the body of my, at least that'll be a thread which is running in the back. But before we do that, let's have some fun. So there's this graph. I guess everybody here, I mean, I know there's a friend of Sean, so certainly I don't think there would be any disagreement with this. How about people model, real models? Is there a connection between beauty and utility of a person? And I would say no, right? So if I was to take a person here, right? So Donald Trump is right here. That's him, right? So if I know somebody's beauty, they don't tell me anything about the utility and vice versa, right? So I would think that this would be the case. Anybody wants to, Ken, or take a stab at it? Be politically incorrect? Yeah, it's true. I mean, so there's so much unsaid here, right? I mean, there's so much unsaid here, right? So right. It's too complicated problem. But people have thought about it. I mean, serious people have thought about it, right? So they even made a movie about it. You seen this movie, Shallow Hal? Yeah? Only Ken has seen it. All right. I mean, so if you've seen it, I mean, the whole premise of the movie is based upon the fact that the correlation structure is right here. So it's all about models, right? So it's it has Gwyneth Paltrow in the starring role, and they're pretty models who are wonderful people. No, not so pretty models who are wonderful people, and they're conventionally pretty models who are terrible people, right? So there's a correlation. It may be available on Netflix, so it's kind of a cool movie, right, to watch. But I don't really know, no. except, and this good. I should practice this better. But I know a conditional distribution, right? So if I condition with respect to friends of Sean, then they are right here, right? So even though I don't know what the underlying prior is, and this talk is going to be about feedback particle filter, so there's the posterior right there. But if I condition with respect to the fact that they know this bloke right here, who is both beautiful and useful, they're themselves pretty, I don't know about this guy, and this guy just put him there, No, I'm kidding. But certainly, I mean, this was meant to be a riff on Anna, who unfortunately could not make it here. I mean, how, look at her, right? I mean, look at her, right? And if you've ever been to Paris, make sure that Anna takes you around. So, like she did with me and my family when we were in Paris, going for a conference. So, she's incredible person, right? So anyway, this is a great pleasure to be here, and with that, I'll get to the main body of my talk. So imagine a problem where you have a cannon, and you load up a model and you shoot her, right, into the space. Right? So there's axis here, there's time, and then there's axis here. Sorry, I mean, I was making this at like 2 a.m. at last night, so this, all right, anyways. So, and then there's x here, so that's the height from the cannon. And then as I shoot up a model, right, then she follows a path. Anybody knows what this path is? The graduate students here? It's a parabola, right? I mean, this is how you learn about parabola, right? So it's a parabola, right? How do you know that this is a parabola? Well, the only way I know it is because, I kind of learned it through a model, which was the Newton's model, which says that, this is the Newton's second law, which says that F is equal to ma, right? I mean, so if I was shooting a model in the space, then she would travel in a straight line, right? On Earth, because the acceleration is a constant given by the gravitational field. So I have this, right? Now there is an alternate description, an alternate but equivalent description of classical mechanics, which all these things go back to the beginning of science itself, which is due to Lagrange. So what Lagrange says is that the trajectory x of t is a minimizer of a certain integral, which is an action integral. So L is referred to as a Lagrangian. It's a cost function which depends upon the trajectory and the velocity. It also may depend upon time. So Newton's second law is equivalent. So Newton's second law is again about a scientific idea of how objects move. Is equivalent to the so-called Hamilton's principle, which says that the trajectories are stationary points of this action integral. All right. So what do you think? Who is prettier? Newton? So if you think Newton is prettier, raise one hand. Nobody. All right, good. The second one is Lagrange. The second one is Lagrange. I was trying to find a prettier picture of Lagrange, but you know. Well, anyhow, this is what Google says. So I don't know.
This is a post-truth lecture.
This is exactly. Nobody thinks Newton. Only one guy, right? Yeah. And how about you two? Okay. Lagrange, both hands. All right, good. So Lagrange wins, right? That's Goa. All right, I'm sorry, guys.
No, but like, no matter what Lagrange looks like, he looks better than you. Right?
Then he that's right.
That's true. I'm sorry.
That is absolutely true.
I my bad. You know, I found a picture of Lagrange on Wiki. Yeah, I'm sorry.
All his pictures are very young. He died very young in a duel over a lady. I mean, you know, how romantic can you?
Yeah. No,
is your definition of prettiness a monotone increasing function of the number of chins you have?
All right. Yeah. So, yeah. I mean, you know, but the beauty is in the eye of the beholder, right? And so, so certainly there's that thing. But so I'll define beauty. But nevertheless, if you crack open a book on classical mechanics.
I think Joseph Louis Lagrange is pretty close to Newton.
Yeah. Yeah, this is the picture, by the way.
Yes.
This is the picture I found, yeah, but I thought, no, this is, I should put somebody.
Yeah.
Illustrate the point you want.
Yeah, exactly, right.
Yeah.
But anyhow, okay.
Queen of the pigs, yes.
Thanks, Mehta. All right, so, but you know, if you crack open a book on classical mechanics, right, I mean, intermediate dynamics or something like that, then, you know, they talk about the Lagrangian viewpoint and how it's more useful than Newton's viewpoint. And so a typical list that they go down is computations are easier. So even if you're thinking about a very simple problem as to how two pendulums move, the computation with a Lagrangian viewpoint will take you a fraction of a time compared to a computation with a Newtonian viewpoint. There's an issue of coordinate invariance. So the Newtonian viewpoint is very much a property of Cartesian coordinates. On the other hand, Lagrangian viewpoint, you know, you can have polar coordinates and things like that. Conservation laws are easier to see. For example, Hamiltonian is equal to 0, and so on and so forth, right? So there's a list that goes down. And for me, you know, the beauty would be, you know, define it as presence of a variational structure to the problem, right? I mean, this is the definition of beauty. And certainly there's a rich history. I mean, there's a scientific idea about looking at minimizers or minimizers in space-time for action integrals, which goes back to the very beginning of science and is still relevant today. So the only difference between the first integral and the second integral is in Lagrangian I have now put in the control input. I've called the x dot is equal to control. And when you have a constraint x dot is equal to u, you have a classical mechanics picture. When you depend upon as well on the dynamics, then you have an optimal control picture, which, you know, goes back again to 1950s. Mm-hmm. And now in the last 10 years, right, there's a lot of excitement around putting an I here, and I means that there are many agents, and so I'm interested in variational structures about problems which have many interacting particles, agents, so on and so forth, right? And there is a sort of number of papers, you know, from last 10 years. I was just, this is not an exhaustive list. I just wanted to sort of put some names. Peter Keynes, of course, right, was hugely inspirational for Sean and myself when we started looking at some of these things. There was a very influential paper by Leslie and Lyons on mean field games. So that those are some names. It's a paper by Brockett on control of Lowell equation, which is along similar lines. There's a nice recent paper by Benshausen where he talks about mean field type control problems, not only game problems, but optimal control problems. And then there's a lot of work and a lot of excitement in the area of optimal transportation, where you're transporting densities or finding maps to transport densities. And I put on Trifon, but Alan Tannenbaum and a lot of other people have papers around these things, right? So this is sort of what I'll talk about, or at least try to give my own very skewed, limited, narrow, personal view of this. And I kind of work with examples best, so I'll just talk about 3 examples here, right, as part of my talk. And again, this is a joint work with lots of students. Rick Logeson, math department in UIUC, and then Sean Main, of course, Max Roginski, Uday Shanbag. And Muriel made this point yesterday about how being in Illinois and starting in Illinois, you have an opportunity to meet and work with incredible people. And she, I could repeat word for word everything she said. I certainly, when I started, I was working on some very, very different kinds of ideas. But just being in this special place, it creates just this synergy where you get to work on some of these exciting problems. So again, I want to be very, very light on math. This is more like a conversation. How are we doing with time?
I don't know. Whatever.
Okay, yeah. So it's more like a conversation, right? So please jump in, right? So I'll not have many, many equations. I'm sure we were all wowed by the great many diversity of equations we saw in the morning around Poisson equations. So I decided to sort of keep it light, right? And the question that sort of drives me is, again, from the point of view of beauty more than anything else, is what's the Lagrangian? What's the variational characterization? And this is again, Googling at night, right? So found this quote to be somewhat relevant to this, right? I don't know what it means. Okay, so you can't have a talk by me and not hear about oscillators. I'm sure a lot of you have heard many, many times about oscillators, but this is n+1 time. Coupled oscillators, and this is a Kuramoto oscillator, which goes back to 1970s. So why do we study this problem? Well, if you're doing motion, classical mechanics, the simplest model that you want to think about, right, the first that we teach a student is the parabola. So in some sense, in dynamical systems context or in controls context, I think this is as simple as it gets. There's a linear Gaussian, but this is a nonlinear case. It's as simple as it gets. So it's sort of a prototypical model that people have sort of studied and applied to various contexts, right? So what's this model? Well, this model has n oscillators. The state of the ith oscillator as a function of time is theta ti, right? So that's the I. And you should think about this state as evolving on a circle, right? So the dynamics of the ith oscillator has 2 terms to it, or 3 terms. So this is a noise term. And then there's a omega I, which is a natural frequency. So left to itself, it's just going to spin around with its own natural frequency. So for the ith oscillator, the natural frequency is picked from some distribution, which is given to you. So gamma is the spread of the distribution. For the ith oscillator, the frequency is fixed. For the population, it's picked from this distribution. And then the other term is sort of the coupling term. This is the non-trivial term. This tells how the population affects the ith oscillator. So in this model, due to Kuramoto, the jth oscillator affects the ith oscillator as a sign of difference of angle. And this is, the reason I say this is the simplest is because this is like a proportional feedback on a circle. So if you want to do proportional feedback on a circle, this is what you do. And then the population affects the ith oscillator as an average taken over the population, right? And then sort of a classical result on this is, sort of the basic result in this area is this phase transition. So if you fix a given level of heterogeneity of the frequencies, so you take 10% heterogeneity, then what it says is given a noise level, there is a critical value. There's a critical value below which the oscillators remain desynchronized. So they kind of move around the circle as if oblivious of each other population. But if you increase the level above this, then there's a phase transition so that the oscillators that start sort of distributed along the circle, you can simulate these things, they will sort of come together and then they'll go around the circle lockstep. So there's this phase transition from, people call it incoherence to synchrony. And then people have taken this and applied it to many, many areas. There's Steve Strogatz is sort of the, he was one of my professors at Cornell, and he's like a very popular, he's helped popularize the subject quite a bit. So when we started sort of looking at these things, so again, the central problem that we would like to think about is, if there's a variational structure around it, right? So we said, well, this is the equation of the Kuramoto oscillator. So let me think of this as a control input for the ith oscillator. So ith oscillator is interested in finding its UIT, and large and limit, what are the appropriate variational structures which will allow me to get controls of this form, right? So in this paper, which appeared in Transactions 5 years ago now, we proposed a game theoretic model. So we said we're going to consider this problem where ith oscillator sort of has its control input UIT, and then the ith oscillator is interested in minimizing its own selfish objective eta I by choosing its own control U of I, where the Lagrangian, if you will, has the quadratic control. So I don't want to do much, I don't want to move a lot, but I would like to sort of look like others. So the ith oscillator pays a cost with respect to the jth oscillator, which has a function which looks like this. So if I am kind of close to you, then I don't pay much of a cost with respect to you. But if I'm far away from you, pi distance, then I pay a maximal cost with respect to you. And so I pay, ith oscillator doesn't really care about the jth oscillator, but it's interested in minimizing average distance away, if you will, from the population, right? So it's a game theoretic problem where one is sort of wants to know what a UI, the control action of the ith oscillator will be, but that depends upon the population at large itself. And sort of the main result that we had was this phase transition diagram. So gamma is the level of heterogeneity in the population. So if you pick up heterogeneous population with say 10% heterogeneity in the frequency, then there's a critical value of the control penalty parameter. So if you make the control effort very, very large, then the ith oscillator says, to hell with everybody, I'm just going to not do anything. I'm just going to shut off my control. So everybody does that as a rational decision, and that leads to everybody paying the same cost. But then there's a critical value of this R parameter above which the ith oscillator has an incentive to deviate away from that. So the game admits many, many solutions, but we could show using the mean field games machinery that this solution loses stability in a certain sense to this solution as the penalty parameter R is varied, right? And this sort of generalizes nicely the result, the classical result for Kuramoto oscillator where this phase transition is observed, right? So again, I don't want to sort of get into the math. You'll ask, well, what's the beauty here? So my answer is, believe me, right? It seemed like I need to put this somewhere, right? Given sort of what's happening. This is not meant to be a typo, right? I mean, I kind of picked it up out of the Google, right? So, of course, thankfully, we don't get away with this. But Saturday morning, I guess I don't want to get into. Yeah, sure.
Look at the opposite objective where they're trying to stay desynchronized.
Yeah.
Synchronized one. Tinnitus, and you're in Germany.
Yeah.
Then they give you an MP3 player that plays you tunes that tries to desynchronize oscillators in your head.
Yeah.
They do a lot of work to try and find the opposite of this. How do you have a metastable state that's synchronous,
right?
And you're trying to put an input in that will destabilize it and make them asynchronous. They also have a Parkinson's treatment based on that principle. It's very called Peter Tass.
Yeah.
But the opposite question is actually very important. How do you keep them unsynchronized?
Yeah, it's a very important question. Now, the problem that you're thinking about there is more like it's a centralized problem. So here we were motivated by questions where, it was more of a game theoretic problem, and sort of the example that was running in the back of our head was this Millennium Bridge example. I don't know if you remember about it. So Millennium Bridge was like, bridge opened in 2000 to mark the celebration of a millennium of the Great British Empire. And the Queen came and she cut the ribbon. I don't know how we are doing on time. I'll tell the story in the evening, all right? Now that I've sort of tempted you, given you I'll tell you a story. It'll take me a bit too long. So that was sort of the game theoretic problem that we were thinking about. It was back of our head. But the utility for variational structures, I think, and this was sort of in various talks that we saw in the morning, I think they provide you with a way to do approximation, right? I mean, to me, that is sort of the message that one should sort of take away. How do you want to get approximate algorithm in contexts where you have large number of agents? And then these variational structures or these variational frameworks of the kind, mean field kind, help you deal with that. And then we had a paper on learning in mean field games, which appeared more recently, where we sort of showed how to apply this to this example. So really, I mean, the message is approx TP, right? So UIT is really some function of the value function, which can be defined in these problems. And the question is, how do you find or approximate this value function? So one can sort of build intuition about approximating this in terms of average quantities. So these are sort of the kind of basis functions that we had in the paper. And then you can sort of, apply various gradient descent schemes to find what the parameters of your optimal policy are. And then we showed that, you can approximate the Kuramoto model, and we showed various convergence results around it. And we in fact showed that for this learning system, you can also recover the phase transition diagram. So there's a complete story. So the second problem, the second example that I want to sort of talk about, Ken was waiting for it, I know, right? Yeah. Is a feedback particle filter. And again, I'm not going to get into sort of, people have talked about it, right? So there's a signal model and then there's observation model. And the most important thing here is that this is Gaussian, right? So this Gaussian assumption is sort of the critical behind everything that we do. P0 is the prior. So this is sort of, again, goes back to 1950s, 60s, right? So Kalman filter is a solution to this problem under the assumption that A is linear, H is linear, this is Gaussian, and this is Gaussian. Prior is Gaussian. So if you have all these assumptions, then posterior is Gaussian, and the Kalman filter gives how the estimate evolves. And again, this is a very nice control theoretic interpretation. So I teach my undergraduate signal processing control class, and we do PI control there. So after they have done the proportional feedback control, I show them this. I say, this is the algorithm that you can sort of implement. It's just to gain feedback on a certain error that you define, which makes sense. And then we had the feedback particle filter, where again you have a very, very similar structure to it, that there's an error that a particle makes, and then there's a circle which has some interpretation, and there's a Stratunowicz interpretation of this SDE, but then there's a gain which multiplies that. All right, so there's a very nice generalization of this, which works now. If A is nonlinear, H is nonlinear, this can be arbitrary and this can be arbitrary, as long as the measurement noise is Gaussian. In fact, X need not even be on the Euclidean space. So this works equally well if you're doing filtering on Lie groups. If you're doing filtering where there are boundaries like roadways, this works equally well. And the beauty, I think, is really derives from, we have a paper in SciCon which talks to Poisson equation nonlinear filtering. This really derives from the appearance of this Poisson equation, which is really the hard part of computing this gain. So you solve a PDE at each time, and then you apply this control here, and then that gives you the feedback particle filter. And the utility, I think, is it's really, again, it gets back to, simulation type algorithms. So, I've been hanging around with filtering folks, and some of them are folks who do sort of this large-scale meteorological models. So as it turns out, in meteorological models, the state dimension is very, very high. They implement Kalman filter, but they don't implement the Kalman filter. What they do is they implement a particle filter version of a Kalman filter that they call as an ensemble Kalman filter. And the reason they do that is because the only thing you need is to find the gain. In a Kalman filter, the only thing that you need to do is you need the variance first to find the gain. I'm sorry, I should back up. Right? In a Kalman filter implementation, what happens is the bottleneck of your calculation is the computation of variance. Your mean has n entries, your variance has n squared entries. It's a matrix, order n squared entries, right? So the bottleneck for finding or implementing a Kalman filter solution comes from finding the variance. Now the only thing you need the variance for is to find the gain. So what they say is we're going to approximate the variance empirically in terms of these particles. And this is one of the ensemble Kalman filter that people have sort of worked with in the past. So this particular ensemble Kalman filter is a special case of feedback particle filter where you're approximating this gain by its best constant approximation. So if you find the best constant approximation of the gain, then what you get is ensemble Kalman filter, which is what people implement, except that now you don't need the structure, right? So this is, I think that's where the utility is. So, we want to sort of really go and understand this from what point of view, Amir? Variational point of view, right? This is a control input to it, It has that coordinate invariance. No matter what coordinate choice I use, I get the same structure. Is there a variational principle underlying this? Is there a way I can find what this control input looks like, right? So this is sort of the system that I could write as simply as possible. This is the control input, and at each time I have to solve this PDE to find what the control input is. So I said, all right, let's make it simpler. So this is model 2. This is the feedback particle filter. I said, well, this is just a number. Right? So forget this number, replace it by dt. So this has all the essential difficulty of what this is, except that this does not have any stochastic processes going in it. Right? So I can do much simpler analysis. Right? And the basic question that I'm interested in is what's the Lagrangian for this problem, right? But I'm going to do this one, right? And as it turns out, this system, the simpler system, has a very nice, clean, variational form to it. So I am moving a particle by applying an optimal control, and this optimal control is obtained as the minimizing control with respect to a Hamiltonian via the Pontryagin minimum principle, right? So PT is my state, that's the density. H is the momentum. So momentum over this trajectory remains a constant. And then UT is sort of the minimizing control. And this Poisson equation is the first order optimality associated with this Hamiltonian. So the question is, what is this Hamiltonian? And that's something I will talk about as I go through the talk. Right?
The first one, you've dropped the noise in the first thing, but you've kept it in the second.
Yes, I replaced this by DD. I want to sort of something simpler, right? So the first question is, okay, you've found a variational formulation or something, but is this useful at all? I mean, people care about this. I mean, certainly they do about the filtering, but why would somebody want to do this? And as it turns out, this is a useful way to do optimization, this simpler system, and I will talk about it. I hope so far I have not had any equations, right? It was not overwhelming, right, in terms of equations. I wanted to sort of get rid of equations, but sometimes, you have to have a few equations. But the next 3 slides, I think I'll have a few equations, but nothing terribly difficult. So what I'll do is I will sort of describe the simpler system for the Gaussian case. So again, the difficulty of doing this problem is to solve this PDE. Are there cases where this PDE has an exact solution? The answer is yeah, Gaussian case. So Gaussian case, you can work everything out, right? I mean, that's the analytically tractable case. So I'll describe that. Then I'll talk about the nonlinear non-Gaussian case, and here's where the connection to optimization comes, and then I will sort of talk a little bit about the variational formulation, right? Yeah, so this, again, some random code, you have to do it, right? Now, if you want to learn, you have to just go and do it. Lower time, that's all it needs, right? So in the Kalman filter, in the feedback particle filter case, if you take your model to be linear, then your feedback particle filter becomes something like this, and if you look at the mean and the variance of this process, so what do I do for mean? I take the mean of both sides. So the mean of this, because it's a linear structure, becomes equal to this, and so the divide by 2 goes away. So that's all I'm left with. They just add up. So that's the equation for the mean, and then that's the equation for the variance. All right? So that's why feedback particle filter works in the linear Gaussian case. So now let's think about the second problem, the model 3, where the h is a quadratic function. So the corresponding result, the linear Gaussian corresponding result for the model 3 is the quadratic. H is quadratic, density prior is Gaussian. So let's look at that, where you have this x bar is sort of where the minimum of h is, and h is positive definite, and c is some affine constant, doesn't matter. So in this case, again, you can solve the PDE in closed form. You can write the optimal control policy. No surprise, it appears as a linear policy. Right? K is the same thing. Is K the same thing, Amir? All right. Okay. Again, I should say the credit goes to all the people who worked on this, who know the details and the devil. But certainly, K is like Kalman game. It's K solves the Lyapunov equation. All right. So there's this. That's the system. It's an affine system. It's a linear system. So again, if you have a Gaussian prior, then it evolves as a Gaussian. And you can look at the equation for the mean and the variance. So the equation for the mean and the variance are exactly very, very similar to the equation for the mean and the variance for the Kalman filter. Right? So that's why we say it's the generalization, or it's a special class, you can say. Or there's a relationship between the two. So in the filtering problem, if your h is linear, then your particle system has mean and variance, which evolves according to the classical Kalman filter. For the model 3, if your h is quadratic, then the particle filter has mean and variance, which evolve according to this system. And if you let this time run forward in time, then xit will converge to the minimum. The x bar where the h takes the minimum value, right? So in the nonlinear case, in the nonlinear non-Gaussian case, the relevant PDE for P is this replicator PDE, whose exact solution is given by up to a normalization constant is of this form. So this is your prior density, and then you're multiplying by exponential times minus THX. So there's a way in which you can describe this model. So there's something called model-based algorithms for global optimization. So there's a whole community around this. These are some people who work in the control community to sample from this distribution.
Simulated annealing as well.
Yeah. No, but there's a difference because you have a whole population which you try to sample from a given prescribed model. So this is like a simple model that they prescribe. There are other kinds of models also people use, but this is like a simple model. So this is typically a way you do these things. You start with this prior density, and then you have a recursive procedure whereby every time you get these weights based upon these things. And then you sample new particles. So if everything you do right, then these new particles at time tn are sampled from this distribution. You let time go to infinity, and you arrive at the minimizer. So this system is exactly doing this, except by using control, an optimal control with respect to something. So you start with this initial prior, but instead of recursively doing the update using importance weights, which are given by this, you find the control input, which is a solution of this PDE, of the Poisson equation. So solution of this, solution of this, solution of this, right, are exactly the same thing. So what this is doing is, this is how I can simply try to explain what a feedback particle filter does, is it's sampling from a given distribution by using or applying control input, right? So finally, the optimal control problem. So this took a while to do, but I think this is at least one answer to this problem. So the problem that we considered, again, is an action integral over some time. Lagrangian is a function of state, which is the density and the control input. And then the Lagrangian that we had to pick up to make these things work has two parts. So this is what we call as a control. This is a non-classical structure in some ways. This is sort of the control cost, because it depends upon u. And then this is the state cost. So this is, in some ways, it is doing what Kuromoto was doing, where you want the ith oscillator to look more and more like the mean of the population. And as it turns out, this problem can be solved for the value function exactly. So the value function for this problem is just the expected value of h. So if you run these algorithms, the expected value of h will continue to go down all the way to its global minimum. And then using that Lagrangian, you can define the Hamiltonian. So this is classical. So this is your constraint. Q is the momentum variable. Because of a relationship between Q and the value function, the Q does not change over this thing, over time horizon. So what you have is you're doing the minimum principle to obtain the control at each time. So this is a value function. So every density, momentum, control, you get a number. So you're trying to make this number equal to 0 by searching over policies which belong in a certain space. So what you do is you write the first order optimality condition for that, and the first order optimality condition for doing this gives you the Poisson equation. So there's sort of many questions. I mean, I just wanted to sort of provide you with 3 example problems, some flavor of what these things do or capable of doing. There's sort of many questions around it. How does this work? Why do you guess this? What's the utility? As it turns out, in the global optimization world, there's a non-parametric class of algorithms. So these algorithms are non-parametric, and then there's a parametric class of algorithms where you're trying to update the parameters of some distribution. So from a variational structure, then these two algorithms become exactly the same. They just the coordinate, which coordinate you're trying to solve the problem in, and then numerics and examples and so on and so forth, right? I don't know why is this relevant. What's after modeling, right? So there's a lot after modeling, right? So certainly, but that's it. That's it for me. Thank you.
Thank you. So it's solved. Do you understand why Poisson's equation comes up here?
In the model 3, yes. Yeah. So, the system is like this. You have an ODE, and then every time you're solving a PDE, right? And the maximum principle optimal control has the same structure to it. Every time you're doing an optimization for a Hamiltonian. So as long as you can define the right Hamiltonian, then that gives you the Poisson equation, right? But this is in the appropriate infinite dimensional space of densities. That's the only difference, right? Yeah. Now, for the feedback particle filter, what's the Hamiltonian? We don't know, because you have a control which depends upon the stochastic process, and I don't know if, and perhaps you guys will tell me, where you inject stochastic processes as part of control.
So go back one slide. So this was like the ODE, the simple problem.
Yeah, this is a simple problem. Yeah. Right, this is a simple problem. Right, this is all the simple problem.
That's frustrating.
This is all the simple problem.
It's not over yet. Okay.
It's not over yet. Yeah. We're looking for problems to do, Sean. There's still hope, right? Yeah.
Any questions?
All right.
Thank you, Prashant.
Thank you.